So their spatial part is symmetric. But that doesn't mean that they are necessarily point-like. It does mean that they will consider their excitation higher in energy than the hadrons we are going to study, that are the hadrons below 2 GeV. So, since the spatial part must be symmetric, this limits the possible dipole states to the one we can say in this table. The first line we find dipole in color triplet, and in the second line we find dipole in the color sextuplet. Then, according to most models, for example, one-gluon exchange calculation, the color sextuplet is not favored, and possibly is not bound at all. So we will not use this type of dipole. We will use only the color triplet type of dipole, which is we can distinguish in a scalar one, the green, in green, and an axial vector one in red. The scalar one is called in Jaffe terminology the good dipole, while the red one, the axial vector one, is called the bad dipole. Okay, so now we start describing the theta quarks. What are theta quarks? Theta quarks are exotic mesons composed of 2 quarks and 2 antiquarks. They can have either explicitly exotic quantum number. For example, they can have isospin equal to 2 or hypercharge equal to plus 2. Or they can have, more commonly, the same quantum number of the normal meson. In this case, they are called cryptoexotics. So, no explicit exotics are known with certainty. However, there are several candidates. For example, here I have put the Pi1 1400, which has JPC quantum number 1 minus plus, which is an exotic combination. And I have put also the Z plus 4430, which is a charged meson that decays in CC bar. So if it exists, it must be a theta quark. Then we have also the cryptoexotics that are obviously more difficult to identify. However, Jaffe, since the 70s, already identified a complete nonet of possible tetraquarks. That is the light scalar nonet. This scalar nonet is composed of the A0 980, the F0 980, the F0 600, and the K 800. The first two are very well established, but the second two not so well, so we will see that their existence is crucial for distinguishing between the various models. So why Jaffe thought, and we too believe that this light scalar nonet is a tetraquark? There are many reasons. The principal are this one. The first reason is the reversed spectrum of the nonet. We can see on the right the pattern of the normal mesons nonet. We can see that we have an isotriplet with light that is lighter, that is more light than all the others, because it is composed of only non-strange quarks. Then we have a strange meson, and then the heaviest one is the isoscalar, which is composed of two strange quarks, one strange quark and one strange antiquark. In the case of our scalar nonet, the spectrum, the pattern is completely reversed, because we see that the isoscalar is the lightest. Then we have the strange meson, and then we have the the isotriplet, which is the heaviest meson. So this is only compatible with tetraquark content. Then there are also other reasons that are the decays. For example, we see that the F0, 900, and 80 can decay in kk bar, and this is a clear violation of the Okubo-Zhang-Zucca rule, because in the normal, if it was a normal meson, it would have only non-strange quarks, so it would decay in strange mesons. Then the same can be said for the F0600 and for relative decays. Okay, so there are three possible different models for tetraquarks. The first one is the compact tetraquark. In this model, the tetraquark has no internal structure. For example, PAG model is an example of this model. Then there is the molecular model. In this case, the tetraquark is made of two mesons that are normal mesons, so they are in color singlet. And then finally, there is the diquark-antidicor state, in which the tetraquark is made up of a diquark and an antidiquark. So let's see why the existence of F0600 and K800 is so important. It's important to distinguish between two of these models, between the compact and diquark-antidicor model from the molecular model. Because if the H0980 and the H0980 are molecular, they do not need to form a complete nonet for the tetraquark, but so there is no need for the existence of the other two mesons. If these other two mesons exist, and they exist at energy like their names indicate, they cannot be molecules because they have a mass much higher of the threshold of their components, so they must be or compact tetraquarks or diquark-antidicor tetraquarks. The latest data from the, for example, E791 and BESS2 experiments, and the data analysis from this experiment seems to confirm their existence. So let's begin to classify all the tetraquark states. We are guided by two conditions that are quite obvious. The first condition is that the tetraquark should be a color singlet. And then, since the tetraquark is made up of two identical fermions, two identical antifermions, they must be antisymmetric under the exchange of the two quarks and the two antiquarks. So we have started by constructing the intrinsic degrees of freedom, classified through the representation of the standard group SU6 of spin flavor times SU3 of color. In the first line we see the spin flavor, and in yellow we can see the exotic multiplets. Then we can see the flavor, the SU3 of flavor, the possible representation of SU3 of flavor, and we can see that the tetraquark can be also not only in singlet or in octet like the normal meson, but they can be also in decuplet, antidecuplet, and in the dimension of and the representation of dimension 27. Then we have the color. The algebra of color is the same like the algebra of flavor. However, only the sign singlets are allowed. And we note that there are two different singlets. Then finally we have the spin, and we note by the spin that the tetraquarks can have also spin equal to 2. Then we describe the spatial degrees of freedom. We introduce the 3 relative coordinates, the one between the 2 quarks, the other between the 2 antiquarks, and the third between the center of mass of the 2 quarks and the center of mass of the 2 antiquarks. We introduce relative angular momentum associated to these coordinates, and we combine all these moments with a spin like shown in the left. For example, we combine the spins of the 2 quarks with the angular momentum between the 2 quarks to give this total angular momentum. The same for the 2 antiquarks. Together they give this S that is not a spin but is a combination of angular momentum and spins. And overall we have the total angular momentum. With this choice of coordinates, it's easy to calculate the parity, C parity, and G parity, because we can follow the same procedure that we can follow for normal mesons. With the difference that we have 3 different angular momentum, relative angular momentum, orbital angular momentum, and here we have this S that is not a spin but a combination of various angular momentum. So then we apply the Pauli principle. We put together the spatial part and the intrinsic degrees of freedom. And so we can construct all the states. Here I have put 2 tables between all the possible states. These 2 tables are one with all the angular momentum equal to 0, and the other with only the relative angular momentum between the 2 quarks and the 2 antiquarks equal to 1. These are the tables that are more useful for the dipole-antidipole limit. And in green we can see the scalar nonets that we have presented before. And here we have a superposition of flavor states, and in doing the superposition we followed the ideal mixing hypothesis. That means that we consider states with a definite number of strange quarks and strange antiquarks. Then, now that we have the states, we need a mass formula to calculate the spectrum. And Professor Iachello introduced in the 90s an algebraic mass formula for the normal mesons that was based on spectrum generating algebra U4 times SU3 flavor times SU2 spin times SU3 color in a street-like model. Then the intrinsic degrees of freedom are standard. The most interesting part is the spatial part, which is described in terms of the Casimir operators of this chain. So the mass formula is this one, where we can see we have linear vibrational trajectory, and a linear rotational trajectory, and we have an explicit dependence on the masses of the constituent quarks. Then we, to do all the the general tetraport case, we should change the spatial port because we have now 4 objects. So we should choose, for example, the U10 or U4 times U4 times U4. This is still a work in progress with Professor Baker. However, in the meantime, we have developed a dipole-antidipole model for tetraports. In this model, as we have said before, we freeze the spatial internal degrees of freedom inside the dipole. So of the 3 U4 here, we have only 1. So we can use the same mass formula developed by Professor Iacchello. And with this condition, the dipole-antidipole states are a subset of the states that I presented before for the compact tetrachord. In particular, the subset with these 2 orbital angular momentum equals 0. And then we have to remember that we use only the color triplet dipole. So nothing. Then this is the mass formula. We determine the dipole masses by fitting the mass formula. And we can show the spectrum of a preliminary extract of the first states. Then it is important to underline it is important that we still have to calculate the decays because we have a lot of states with a low energy, and without the decays we cannot say which one the experimentalist could see or not. So this is still a work in progress. Then I can start to speak of the baryons. So the baryons are another obvious application of the dipole. In this model, in the quark dipole model, the interaction inside the baryons are simplified, and the predicted states are much less. This could be a partial solution to the missing resonances problem. Again, we can use only the color triplet dipoles because the baryon must be color 0, must have color 0. So here we have the SU6 states. We have a symmetric state and a mixed one. Combining with the orbital with the spatial part, we find this pattern. So the 56 has always even angular momentum and positive parity. The 70 has always odd angular momentum and negative parity. If we decompose the SU6 states in SU3 times SU2, we find that for example, that the singlet can have only a scalar dipole, and the decouplet can have only axial vector dipole. These are the classification of all the states in the quark dipole model, again by applying Pauli principle. Okay. In green there are the baryons with the scalar dipole, and in red we have the baryons with the axial vector 1. This is a mass formula that we developed for the baryons. Again, it has been inspired by Iacchello's mass formula. We have again the linear rigid trajectories. We have the dependence on the dipole masses, constituted dipole masses, and we have the Casimir of SU6, SU3, and Okay, so the main feature of the mass formula 2, the linear trajectory, and here we have compared our result of our fits for the baryons and for the mesons with some results from the theory, from string-like models, and we can see that they agree quite well. Then we have the other main feature is the explicit presence of dipole mass difference, and this mass difference can be compared to the one obtained with other models, since they are they are more or less model independent. Here in the last line we can see our results, and the other lines the results from other models. We can see that, for example, the difference between the axial vector non-strange dipole and the scalar non-strange dipole is more or less in the same range of all the other models. We have also calculated all the other mass differences, while other models usually don't calculate them. So this is the spectrum that we obtained, that is still preliminary because it's a work submitted to FISRFC. We can see that the results are enough good. Then for the conclusion, in green we see what we have done, and in red what we plan to do in the future. We have constructed the complete set of states for the tetraploid, and we have also the special case, dipole-antidipole. We have a mass formula only for the dipole-antidipole limit. We need, we are working on a mass formula for the general